and go from current slide. Now, I thought I hit the projector, but evidently it didn't take. Okay. A couple things while we're waiting for the projector to come on. I guess y'all know the good news, bad news situation next week, right? The good news is next week is 4th of July, national holiday, state holiday. The bad news is it falls on a Wednesday, so we'll miss class. So get over it. Okay. And so I hate missing class, especially in a course like this that we already, the first day of class I wasn't here for, and then we missed a Monday with Memorial Day. It's going to be cramped trying to get everything done. All right, we finally got the projector back. There was only one example presented in this section, so let's pick up and go from here. We did example 1, example 2. I've got today, we're starting example 3. Any questions on anything we've done so far? Okay, so let's pick up with example 3. Let me get my pen activated. All right, example 3. And by the way, this example, it says, see larsoncalculus.com for an interactive version of this type of example. Maybe not exactly this one, but this type of one. Okay, so here's what we've got. Find the integral of dx over x squared plus 1 to the 3/2 power. Now, where would you begin on a problem like that? Do what?
For trig substitution, we want to make it a square root.
Right.
Right? Because it's raised to the 3/2, so we can square root it, raise it to the 3rd, right?
Yeah.
And that would be tangent.
Okay, yeah. Our trig substitution. You might try some other substitution. Nothing's going to work. Okay? There's no way that I know of to work that except for a trig substitution. And since you have the a squared plus u squared type form, that is perfect for the trig substitution. If it's a squared minus u squared, sine substitution, u squared minus a squared, secant substitution, x squared plus a squared, or anything similar to that is trig. It's tangent. So what will be your substitution? Let A, is that what you said? What is A representing? Your new variable? It's okay if it is. That's what, huh? Yeah, okay. Okay. All right. Usually the A is the 1, and the U was the X. So I'd rather not use those. Remember on this one, now on most of your other substitution, you pick a new variable to represent something here. With the trig substitution, that's not what you do. You pick this variable to represent a trig function. That's sort of the change. That's a different way of doing it. And what would be, so what is your variable here? X. Let X equal, and you said it before, the which? Huh? That's your, what you told me what trig substitution was.
Okay.
Tangent, and usually we use a theta there, but you can use anything you wanted to. Your A here is 1, so you don't have anything in front of it. If there was an A there, you would do a tangent theta. You don't have that, so it's just tangent. Do you like theta, or would you rather have something else? Okay, tangent theta. Okay. Well, you got some things to do to that then. And which way you want to go. I go horizontally by expanding on the x. I go vertically by doing my dx. You don't have to do that. That's just my little way of doing it so I don't forget to do something. So what you want to do?
We have to do both.
You're going to have to do everything at some point.
So dx equal
Okay, let's do that then. Then I'll put then dx is equal to secant squared theta, but always with the d, make sure you put another d theta. Okay? That's pretty ugly in front there, isn't it? Let me make that look a little better. Okay, I'm writing faster than I'm talking faster than I'm writing, something like that. Then dx is equal to that. Okay? Next. Okay. X squared is tangent squared theta. And then if you want to do a 1 to that, there's that. And then you ultimately at some point or another are going to be taking the square root of that. What is tangent squared theta plus 1, by the way? That is secant squared theta. You're absolutely right. Okay? And then, if we want to take a square root of it, that would be, okay, so the square root of this thing is secant theta. Okay. And here's Connor. We're doing example 3 on page 543. Okay? Now, and here's Preston. All right. All right, good deal. All right. Yeah, nobody else has come in. And then, since you're cubing that, that's the square root, that cubed would be, so this thing cubed would be secant cubed theta. Okay? So, I think we got that taken care of. Okay? Now, the one other thing I suggest that you do, this is just a suggestion here, but I think it's a good one, draw your little triangle. Okay? Always try to have a right angle or something that looks close to a right angle in it. Okay, go to your original thing here and do tangent theta is equal to x, and it happens to be x over 1, right? Okay? So, put your angle theta in here, and what in the world is tangent theta here? What is tangent? Opposite, which would be your x, over adjacent, which is 1. And what does that make your hypotenuse? Pythagorean theorem. X squared plus 1, which is your radical here. Oh, isn't this nice? Okay. Maybe or maybe not, but yeah. So you really have everything you need now. So with those substitutions, let's fill in the integral. Your dx is secant squared theta d theta. That's your dx. Direct substitution there. This thing cubed to the 1/2 power, that's this over here, that's secant cubed theta, right? So what does that turn out being? 1 over secant theta. Now, before you start panicking and say, I don't know, the antiderivative of something, you know, yes, what is 1 over secant theta? He whispered it. Reciprocal identity. What is secant theta? 1 over cosine. So this, since it's in the denominator, cosine will be in the numerator, and I think even I can do that one. The integral of cosine theta d theta. What would that be? Sine theta. What else? It'll have a plus c in it. Let's just wait a little bit and do that. But let's go back. Okay. Now, here's a problem, Houston. Our original problem was in x's. You give me an answer in thetas. Okay? Now, given what we have here, it's going to be pretty nasty to try to figure out what that is in terms of sign of x. But you know, that's where the little triangle comes into big play here. Because can you give me sine theta based on this? What is sine theta? Opposite of our hypotenuse. There it is. So this will be, in terms of the x variable, x over square root of x squared plus 1. Okay? And now you can do your plus c if you want to. So you could have done the plus c earlier. That would have been okay. But I usually like to wait till the end to do it. But just don't forget to do it. See how that works? That's why the little triangle is pretty helpful. So you don't have to go back and say, okay, now what would be sine theta in terms of x's here? And so I think you're. Let's make sure they did it right in the book. That's the x over square root of x squared plus 1 plus c. And you back substitute. And they did do the plus c up there too, which is okay to do. I just didn't want to get it in some form that I didn't want it to be in. All right. Now, any questions on example 3? Let's move on to example 4 then. I'll clear all the ink. And we'll do example 4. Okay. Evaluate this. A couple things are a little different here. One is this is a definite integral. From root 3 to 2, the square root of x squared minus 3, another little thing different here, divided by x and a dx. All right. Now, are there any little tricks that you want to try first on this? If there, huh?
In terms of like being on the same line. So
What's that?
In terms of being like on the same line and not over each other.
Right. Okay. And what might you try to do for that? Any ideas?
Change x squared minus 3 to x squared minus 3 to the 1/2, and then change x to the negative 1.
Okay, but you still got x minus 3, x squared minus 3 to the 1/2, that to the minus 1. You're not going to be able to combine those in any way because you have different arguments, you have different bases. So it's a good idea. Now, if these had been reversed, then a substitution would be great. That u equal x squared minus 3, du is 2x dx. If this is up there, this is down here. Yeah, we can go to town with that, but not with them reversed like this. So good idea, but I don't think anything's really going to help you there. Don't mean to be stomping your parade, but I'm afraid I can't think of anything else. At first I thought, well, let's rationalize the numerator. Multiply the numerator by square root of x squared minus 3 in the denominator. Now you just made the denominator worse, and the denominator is where you'd like it to be sort of simple. So I don't think that will help much either. I considered it, but I don't think it's going to work. So if all else fails, and especially since you have some things that look like easy things to do trig functions on, I think maybe a trig substitution might be in order. Okay? And what would be the classic to use this for? Use for that type of problem. That would be the secant. So what is your substitution? Let x equal?
Root 3.
All right, very good. That was the other thing that's different about this one. We don't have an a squared here, okay, unless you think of that as root 3 squared. So that's exactly what you need to think of. So that's going to be your a, the root 3, okay, times what? Secant theta Okay? Now, I usually say let's go in either of two directions. You choose. Okay, dx then is equal to root 3 secant theta tangent theta d theta. All right, we've got our dx now. That's checked off. Let's do some other things with this. What would you suggest we do? Square it. Okay, so that would be x squared is equal to 3 secant squared theta. Okay, then what are we going to need to do with that? Subtract 3 from it. Okay, we can do that. And that will be 3 times secant squared theta minus 1, which is what? Second? That is exactly 3 tangent squared theta. Okay? And we're taking a square root of that, right? And the square root of that would then be, I guess I could go back and put square roots over everything. And the square root of everything here would be the square root of 3 times tangent theta. Okay? I think we've done all the damage here we can do, right? Well, one other thing might you want to do? Yes, don't forget your little triangles. And they can be ugly little triangles. You know, that one's pretty ugly. Put your theta here. Make sure you understand that's supposed to be a 90 degree. And you had, I'm going to rework this just a little bit. This would be secant theta is equal to x over root 3. Right? Okay. Now, with that in mind, tell me what secant is. Is what?
1 over cosine. Hypotenuse over adjacent.
Hypotenuse over adjacent. What's your hypotenuse up here? Okay, that long one here, that's going to be your x, and your adjacent side is your root 3. Which means you can fill in the opposite side. And what would that be? Yeah, it's going to be a square root. X squared minus 3. X squared minus 3. Right? Which is exactly what you got under your radical right there. There is your radical. Okay, that's your numerator there. All right. That may make you feel warm and fuzzy inside, but I'm not sure it's going to help any, but that's what you got. Okay, let's start plugging and chugging then. We've changed our variable. Do we need to change our limits? Yeah, I'm afraid so. So when your x, and these are values for x's, remember, when your x is root 3, can x ever be root 3? What would your secant have to be? If x was root 3, secant would have to be 1, right? Secant theta is 1. Where is secant theta equal 1? Okay, multiple choice, huh? I've got to choose. Oh, let's see, which do I go for? Okay, which? 0, you're right. Because remember, secant is 1 over cosine. Cosine is 1 at 0. So our new integral here, I'm going to write it down here, would be your theta is equal to 0. And then let's do the other one. If secant theta root, I'm going to do it up here. 2 is equal to root 3 secant theta. What I did, I plugged in the x here and then wrote in the rest of it. So that means secant theta is equal to 2 over root 3, right? And where's that? Okay, that would be the same as cosine theta is equal to root 3 over 2, right? And where is that? Pi 6, is that what you said? That's absolutely correct. So this is going to pi 6. See, we changed our variable now, and we don't have to go back and worry about that anymore. We don't have to go back and back substitute on this one because we'll just use our new limits here in thetas. All right, now let's figure out what we've got here. That root square root of x squared minus 3, that was this, which was this, which was this, which was this, which was that, right? So that's going to be, I'll put the radicals on the inside to begin with. The square root of 3 tangent theta, right? That's the square root thing. The dx is this, another square root of 3, so that's going to make it a 3. I think I'll pull that on the outside now. Secant theta times another tangent theta, so that'll make a tangent squared, and then we'll have a d theta. So that's our numerators. You see what I've done? Was that magic? You saw all, you said yes, it was magic, right? Okay, I see. Have you see where all that came from? Okay. Now, divided by x. What was x? It's the square root of 3 secant theta. Well, looky here. The secant thetas disappear. I can take this root 3, and I should have not done a thing with the other one, made it a root 3 out here. Okay? So basically, those disappeared, and the other root 3 came out. However you want to do it. Winds up with a root 3 out there. Okay, now, here's my integral. Let's write it. So clear this up a little bit. It's root 3 times the integral from 0 to pi 6. My pen is really slow. Tangent squared theta d theta. Okay. Now the first thing I want to ask myself, is tangent squared theta the antiderivative of any function? No. Secant squared theta would have been tangent theta, but not tangent theta to squared theta is a secant theta. Okay, so don't try that one. Now, we went through, last section I think it was, or somewhere earlier, we went through how to do some other things here. What I would be real tempted to do is just go to a table, okay? Because I don't really like to memorize all these things or stuff like that. Wait a minute. Wait. Yes, let's use the Pythagorean. I just thought of that. This is the same as the root 3 times the integral, my root 3 will do, from 0 to pi 6 of, and what is tangent squared theta? Secant squared theta minus 1 d theta. Now, that one we can do. I just said that is the antiderivative of something. So this is root 3 times the integral from 0 to pi 6, sorry about that, of secant squared theta d theta minus the integral, root 3 times the integral, from 0 to pi 6 of 1, or just d theta, right? Can you do the first one? What's the antiderivative of secant squared? Tangent squared. Wait, tangent. Okay, yeah. Okay, so that's root 3 times tangent theta, because the derivative of tangent is secant squared, and that's evaluated from 0 to pi 6. I don't know why the pen is so bizarre right now. 0 to pi 6, okay? And the second one is just what? Minus root 3 times theta. And that's evaluated from 0 to pi 6, okay? Goodness, this is slow. All right. Now, what is tangent of pi 6? Okay. I'm going to erase some of my lines up here. They're not really doing me any good, and I'm afraid they'll just get in the way if I don't erase them. Okay. Let's draw our good old favorite unit circle. Okay. Ooh, that's not a very good one. Okay. Now, here is pi 6, 30 degrees basically. Right. Now, this isn't drawn very well. The y value here is 1/2. The x value is √3/2, and that's just 1, right? All right. Now, the tangent of this, and remember this is 1/2 √3/2, 1. Tangent is opposite over adjacent, which is 1/2 over √3/2, which is 1/√3, right? And I'm going to write it just like that. I'm not going to write it √3/3. I think you see why, right? Okay, good. Oh, minus, what's the tangent of 0? Okay. Yeah. Tangent is sine over cosine. What's sine of 0? Zero. So tangent 0. Okay. So I took care of the 0 there. So there's the first. I think that's just going to be 1. And the second is going to be minus √3 times pi 6. And 0 will be 0 again, right? So what do we have? 1 minus, I can't think of any better way to write it, is pi √3 over 6. Now the reason I put the pi in front is just my preference, is because if I put it at the end, I'm afraid I'll look at that and think it's the square root of 3 pi. And it's not. So I put the pi in front. That to me is the answer. Let's see what they got. If I can find the problem, there it is. 1 minus, they put the pi after. I don't like doing that. They got the same thing, and then they figured out what it was approximately. A pretty small number. Okay? And on this one, we did use our, no we didn't. I'm not sure we used a triangle. If we had been going back substitute, it would have been a great thing to have. Okay? But as it turned out, we didn't need it. But still, not a bad thing to have up there, in case you do. Any questions on that? Does it make sense? Any questions? None? Okay. All right. Now, I'm trying to see why they have the answer written in 3 different places. I don't know. I guess oh, I see what they did. If they hadn't changed, if you hadn't changed these here and just left it as an indefinite integral for a while, and you got down to this stage, which is this one, without the things here, √3 tangent theta minus √3 theta, okay? Then your tangent, your diagram would have come in pretty handy up there. Because tangent would have been square root of 3, square root of x squared minus 3 over √3, but square root of x squared minus 3 over 3, all of that. You could have done it that way, and then gone back and plugged in your x values. I don't recommend it, but it's doable that way, and that's what they show you here. You could have done it that way. You get the same answer. Okay. Now, why did they do that? Do that? Oh, good thing. The intern comes. Okay. Yes. And he's dressed like an intern.
Yeah.
Okay.
Did you want some coffee?
What's that?
Do you want some coffee?
Yes, please. I thought you said coffee. I was going to say please on that too.
Right.
Okay, there, no problem. Okay, so here's William. If I can find you, there you are. We just finished example 4 on pages 544 and 545. It took 2 pages for them to do it. Okay? Now, there is an important thing here they have on the second half of page 545, and I think they leave that out completely. Let me just see if they do. Yes, they do. Okay, so let me go back and clear this. All right, to clear it? Okay. This, to me, deserves a little bit better than a little remark here. But it says, going back to chapter 5, which wasn't done in this class. What if you had an integral that looked something like this? The square root of x squared minus 2x dx. Okay? X squared minus 2 I have no problems with. We can do the secant substitution like we just did. Okay? X squared minus 2x, a big boo hiss. I don't know what to do with that. Okay? Their suggestion here, complete the square under the radical. Do you remember how to do that? It's an indefinite integral, so it's the square root of, here's your dx. Well, your x squared minus 2x, that's fine. Okay? You remember how to go about completing the square. Take half of this coefficient, which would be -1, and square it. Right? What's -1 squared? +1, right? I don't use that pen. +1. Okay? But if I add 1, I have to do a -1. Okay. Now, that looks sort of stupid, doesn't it? I mean, what's the point in that? Well, here's the point. This will be the integral of the square root of. This is now a perfect square trinomial. That's why we completed the square. That would be the square root. The perfect square trinomial would be x minus 1 squared. Remember that? Okay? Then you got your -1 here. Okay? What does that look like it might be? Second? And which one? Secant again. So here we'd let, but here's the difference now. This time we let x minus 1 equal 1 secant theta. Okay. And that's a little bizarre too, isn't it? And you could go on and do your dx is equal to, that 1 doesn't interfere with that, and that would be secant theta tangent theta d theta. Okay. You could go on out here and do your other stuff just pretty much like we did before. You know, carrying on just like we did before and going from it. Now, if you do a triangle, remember you have to be fair and do the triangle. It gets uglier all the time, doesn't it? Here's your theta. So what this is hypotenuse over adjacent. So that's 1. Adjacent's this, and this is x minus 1. Okay? And then this is the square root of, yeah. So basically, this winds up over here, the square root of x squared minus 2x. Just like what we started with. Okay? And that's always good. And it's kind of good to see Tyrell come in, isn't it? Kind of a little bit. Good deal. Okay. All right. They didn't carry it forward, but that's what you do. Okay? And they continue like that. So, don't get discouraged if you don't see it. Try completing a square. Follow that on through. I think you'll find that you can do something with something like that. Okay? Just to throw it here, right? A little remark at the end. This is how you do really difficult problems, you know. stuff like that. All right, and here's Nicole. Okay. All right. Now, we'll get to the last slide, which is basically reminding you what we just did. Special integration for the trigonometric substitutions can be used to find three integrals listed in the next theorem. These integrals will be encountered several times. Oh, my goodness. You know what? I mean, it's just basically, they're giving you the results. If you had done these integrations, this is what you get. You would have gotten it if you go back and done it. So they're giving them to you. Yay. I mean, I think I just as soon do it rather than, I'm surely not going to memorize those things, because I guarantee you I'm going to get a sign or an order or something out of place. Forget to do something in front. So they just give you these three special integration forms. You know what? If I need them, I'll look them up in a table. If I don't find this book and remember what page they're on and do it, I'll have a table that has those in it. So, anyway, I thought they were just reviewing the ones we'd already done, but you get them from the way we just did things. But as you can tell, they're going to be a little bit hairy getting there. But these are the results. Okay. Now, applications. I didn't realize we had another page here. Let's go for it. All right. Example 5 here. Find the arc length of the graph of this thing from x equals 0 to x equals 1. Okay? And by the way, that thing is a quadratic expression. It's a simple parabola. The only thing that's a little bizarre about it is that you squished it. Okay? That when x equals 1, you're at 1/2, not at 1. Okay? So it's a vertical shrink, is what we call that. And we want the arc length of that. Now, that's interesting. They give this to you now because in Cal 3, you'll do arc lengths, okay? And you'll be doing this all over again. But now they're going to tell you what it is, okay? And they, as they say here, no, I'm sorry, we already did that. I'm sorry. This is Cal 2, we did that. So we've already done this. Sorry, I was taught so many different calculus classes on thinking this was the 3 years into. Okay, we already did this. And you remember how that comes out. Remember the arc length is one that you really have to really struggle with sometimes because what was the arc length formula? Do you remember that?
Oh, you subtract the furthest right one.
What's that?
You subtract the furthest right one from the left one. Is that what that was? Remember?
I'm not absolutely sure I know what you're meaning. You may be right. You're doing a dx here, right? Yeah. Okay. And so your x's is certainly going from 0 to 1 since you're evaluating from that. You're going to be a dx. But remember your little segment here that you're evaluating is has I can't think of any way but reasonably simple to do it without just going back and just remind you of this. It's the square root of, remember it had a big old square root in it. Wasn't it something like 1 plus f prime of x squared? Wasn't it something like that? Remember? And remember what we did. If we blew this up, you have just blew it up and get rid of it. This is a remember your arc length, if your function was looking like this, and you're doing the arc length here, I'm not drawing this too well, the tangent line here would be dy over dx. Okay. The length of this line here, not tangent line, secant line, would be okay. That line there, the length of that line would be dy squared minus dx squared plus dy squared. The square root of that would be the length of that line, right? Remember that? Okay. And then we divided both sides by, and this is all in the square root, dx squared, and by dividing by that, we multiply by dx. The integral here then came out being this thing. Remember? And dy dx is f prime, and that's squared. So remember, we had that really miserable looking thing. And I said at the time, to do these analytically, you have to come up with a function whose derivative squared with 1 added to it is a perfect square, so when you take the square root of it, you can do the integral. And that's a tough thing to get, you know. Well, that's what we wound up with here, isn't it? Okay? So let's see what happens if we do this. What is our f here? So f prime would be what? X. And f prime squared would be pretty easy. X squared. So what we have here is the integral from 0 to 1 of the square root of 1 plus x squared dx. Okay? If this had been back in chapter 7 when we were doing this, we'd have thrown up our hands and said, but we can't do that. You know, there's no tool. Now we got the tools to do that. And what would you use? Say again? Tangent, exactly. So how would you do it? Let x equal, this is, you know, remember on these substitutions, you let the variable here be the let, and you introduce the substitution variable here. And what would it be? Let x equal tangent theta, because your 1 is your a here. Then dx is equal to secant squared theta d theta. Okay. And if you carry this on through, 1 plus tangent squared, right, would be secant squared. Square root of that would be secant. So this radical here of 1 plus x squared would be secant theta. Okay? If you draw your little triangle here, which I highly recommend you do, here's your theta. And from this being x equal tangent theta, x over 1 is tangent theta, so that's opposite over adjacent, which makes your hypotenuse 1 plus x squared, the square root of 1 plus x squared. So full circle, we got everything covered now. So let's start plugging in. Oh, we didn't change our variables, did we? When x is equal to 0, what must theta be? Zero also. So our new integral will be 0 to, when x is equal to 1, what is theta? Pi fourths. Very good. Now we're in thetas. Okay, so let's plug in what we've got. The square root of 1 plus x squared is secant theta. And your dx is secant squared theta, so you have secant cubed theta d theta. Wow. I didn't see that coming. Okay. And that's what we got, folks. How do we do that? My fallback is, okay, so let's see if there's anything else we can do that might help us to do this. No. Yeah. If you pulled out a secant squared, that's a derivative of tangent, but then you wouldn't have a tangent in there. Changing the secant square to a tangent isn't going to help you. I think this is one that I would look up in a table. Okay? I think in this book the table's in the front, isn't it? Basic integration formulas, and do they have a secant n? I don't see one. Do this. Okay? Let's see if the back of the book has more tables. I don't think so. Goodness, this is poor. I'd really like this book up to this point. Most calculus books that I know of have big old tables in them. You know, 2, 3, 4 pages. And I don't see them anywhere in here. Do you? Can't believe this. This is usually a pretty good author. And I just can't believe. Ha! Found them. Appendix B. And of course the page number is really helpful. A3. How do you know what page number that is? Okay, let's go to our, this turned out being longer than what I had planned to. All right, here we go. On one of these, A5, the number 69 is the integral of secant n theta, secant n u, okay? Now, they say go back to example 5 and 8.2 and you'll see this one. That to me is the same as going to a table. Okay, so let's write down the answer from the table. This will be secant to the n minus 2, where our n is 3 here, so that would just be secant theta, tangent theta, yeah, where did that go? Tangent theta, okay, over n minus 1, which is over 2, okay, plus n minus 2, goodness gracious, this is aggravating, which was 1 over 2, n minus 1, times the integral of secant theta d theta. Oh, sorry. All right. Which then requires me to look at another one, and this would be in the front of the book, but since I'm on the same page, this one right here, and by the way, this would be secant theta tangent, 1/2 secant theta tangent theta plus 1/2, and then the secant theta by itself is the log of absolute value secant theta plus tangent theta. Okay, and we'll evaluate those from 0 to pi4. so aggravated at this thing. Okay, I think I've got it all in there. Okay, so let's do our evaluation. Anyone recall, do I recall what secant of pi force is?
2 over root 2.
It's what?
2 over root 2.
2 over root 2, is that what you said? Which I think is root 2, right? Yeah, that's it, exactly. So it's 1/2, so that would be 1/2 of root 2. And what's tangent of pi force? 1. Okay, I can handle that. Plus 1/2, aggravating, the log of absolute value. And we said already secant of pi force was root 2 plus 1. And you don't need absolute value bars anymore. Say again. Yeah, you have to subtract the 0. Say again. Huh? Yeah, that's what I said. You don't need the absolute values because they're both positive, yeah. But we have to evaluate at 0. You're so used to saying, well, 0 is going to be 0. Let's verify it is. Well, secant of 0 is not, but tangent 0 is. So that one's still 0. And secant 0 is not. Secant of 0 is 1. And tangent of 0 is 0. But the log of 1 is 0. Okay, so this is our answer. 1/2 root 2 plus log absolute value. You don't need absolute value, root 2 plus 1. Which I'm sure they're going to give us an approximate answer to. And let's see if they do. It's 1/2 root 2 plus log of root 2 plus 1. And they give an approximate answer of about 1.148. Okay. Any questions on that one? Let's see how they did it. This is how we did it. Let's see if they've thought of any shortcuts or things that would look a little better. Okay, they just go back and say arc length is the interval from 0 to 1 of square root of 1 plus f prime squared dx. Same thing we did. Okay, that is your arc length formula. Okay, so that would be the same as, since f prime was 1/2 x squared, f prime was x, and f prime squared would be x squared, so now you have the square root of 1 plus x squared, which is a secant substitution. They didn't show all the things that we did, but go back and do, we did them, and you get secant cubed. They also changed the limits to match this, and that's exactly what we got. So we got to that step, and then they magically said this is the answer, okay? And that is the answer we got from the tables, evaluated from 0 to pi force. They're skipping tons of steps here, and this gave them 1/2 of the square root of 2 plus log of square root of 2 plus 1, which they give an approximate answer of 1.148. Okay, good deal. They don't do example 6, and after that one, I'm almost not wanting to do it myself, but let's do example 6 fairly quickly if we can. Comparing two fluid forces. This sounds like fun. A sealed barrel of oil weighing 48 pounds per cubic foot, that's the oil, is floating in seawater weighing 64 pounds per cubic foot, as shown in this figure. Hopefully you got your book and can see the figure. I don't want to draw it, okay? The barrel is not completely full of oil. Now, I kind of don't like, okay. With the barrel lying on its side, the top 2/10 of a foot of the barrel is empty. Okay? Compared the fluid forces against one end of the barrel from the inside and from the outside. Assume the radius of the barrel is 1 foot and the barrel lying on its side, and with the barrel lying on its side, the top 6/10 of a foot of the barrel is above water. Oh my word! I'm beginning to think more and more about the wisdom of not doing this and skipping it. Okay. I'm not about to try to draw the barrel in the water, but I think the figure at the bottom explains everything that we need to do here. Okay? And I'll try to reproduce that one, but I'll admit, a really lousy job. Okay? So the first thing I'm going to do is try to draw me a circle. That's not a very good one. I'm going to try to bisect that with my axes, and that's not a very good job. Okay? And we were told the barrel is 1, 1, minus 1, 1. Okay? 1 foot radius. All right. Here is okay, it's Brendan.
Yes.
Okay. All right, so we're getting a pretty good attendance today, finally. Okay. Now, the top 2/10 of the barrel does not have oil in them. So that means, okay, sorry. Let me erase that because that's not exactly what I wanted to draw. Okay. The top 6/10 of a foot is above water, so that means 4/10 of a foot. So there's half a foot here. So the water line is here. Okay, that's the water line. And that's going to be 4/10 of a foot, 0.4. The top 2/10 is air here, so that means the oil goes up to 0.8 feet. Okay. Yeah, feet. Okay. Now, and by choosing the origin to be the center of the barrel, you can define any point on the barrel by x squared plus y squared is equal to 1. Okay, that's by making a circle of radius 1 there. Okay. Now, to find the fluid force against the end of the barrel from the inside, that's from the oil side, okay, and what I had paused that before, when it says a sealed barrel of oil weighing 45 pounds per cubic feet, my question was, is that the barrel and the oil, or is that the oil? Usually you refer to the density of the oil itself. So I think they're talking this is the barrel and the oil. But they're not real clear on it. Okay? And without going through all the force thing again, let's just use the thing they gave us. The force on the barrel is the density. And I think that's the oil in the barrel, but I'm not sure, but that's what we're using. And we're doing this, integrating this. No, this is the oil, because we're integrating it from -1, okay, I didn't put my minus sign down there, to 0.8, because the oil goes to 0.8, okay? and the h of y, how high you are, okay? Your height here is going, okay, from -1, okay? Let's do a little segment here. We're doing dy's here, okay? Here's your dy, okay? Now, how high are you from the bottom, okay? It's your height y plus 1, basically, okay? How high you are from the bottom is your -1 minus y. Is that not right? No. Minus y minus 1. I think I said it right the first time. No, the y is already negative down there. So it would be y minus a minus 1, which is y plus 1. Okay? If y is negative, it's that negative number plus 1, and that would be your height. That makes sense. If it's up here, it would be your height here plus 1 up here. So yeah, I think it's y plus 1. No, it isn't. They say it's 0.8 minus y. Okay, I guess I don't know what h they're talking about. Okay. Without going back and doing all this over again, yeah, 0.8 is definitely the high point, minus y. Yeah, okay, that's what they're dealing with. Whatever y you have here, the height of the oil above that, okay, that's what they're doing. That's your h. The h of y is this, from here to wherever your y is, okay? And that's 0.8 minus your y. And if your y is negative, okay. Still not convinced on that, but 0.8 minus y, that's what they're calling the h of y. Now the L of y, that's the length of this thing here. And what they're doing is, if this is your y value here, okay, it happens to be negative here, this length here is, this is your y, this of course is 1 always, that's the radius, and this length here would be the square root of 1 minus y squared, okay? And then you got 2 of them, so that's where the next thing comes from, okay? So that's where this one comes from. I'm going to put the 2 out front, 1 square root of 1 minus y squared, okay? And then the last one is just your dy. Okay. Now, okay. I hope that you can see, let's do the 2, and that's the density. I'm not sure I buy that symbology, but that's what they have. No, using a weight of W is equal to 48. It's treating that as if it's a weight. I think they mean density. Because this other stuff is calculating your cubic feet. So I don't like their terminology there. But it's the 48. Now they are treating the two separately. But this is going from -1 to 0.8. Okay, that's your integral. And then the first integral is just going to be your 0.8. So let's multiply this and make it 1.6 times the square root of 1 minus y squared dy. And your second integral is going to be minus a 2w times the integral from -1 to 0.8. And that's going to be your y times the square root of 1 minus y squared dy. Okay. Now, I'm real tempted just to hang this up and make this for the student. Okay. Multiply 1.6 by your 48. I didn't write that down. That's density, not weight. Okay. This part you do substitution. Which one? Anybody? Huh?
Most complicated.
I'm sorry?
The most complicated.
Is it complicated? Is that what you said?
Not the most complicated. Wait, what was the question?
Okay. What trig substitution do you use here? Yeah. Anybody? Classic sine. Because isn't 1 minus sine squared is cosine squared? Yeah, that's going to be a sine. What would you do here? A regular substitution. Let u equal 1 minus y squared, du is equal to 2y minus 2y dy. That's going to do perfectly with a regular substitution. So this will be the trig substitution. That would be your regular substitution. Okay? And they both work out pretty well. Yeah, you have u to the 1/2 and other stuff in there, but it's not bad to do. So let's do it to it. 1.6 times 48, they say is 76.8, so I'll take their word for it. 76.8, that's going to be the thing in front of here. I didn't want to do that though. We said the substitution here was let y equal sine theta, right? The reason I paused there is now we have to change our limits, and they don't do that. Clever people that they are. Oh, you know what? They don't do a thing to it. They don't show you how they integrate it or anything else. They just say, oh, and here's the answer, which is yuck. I don't buy that at all. But then they do the forces from the outside, and from the outside, you're only going to 0.4. So you set up your same type thing as before. Now the force from the outside would be the next W, which is seawater, 64, you would use on that one. But you go from -1 to 0.4. And then this is 0.4 minus y, and the rest of it is pretty similar. And that's all they do is show you how to set it up and where you go from there. And they don't show you how they evaluate the integrals or anything else. The details of the integration are left for you to complete in exercise 64, which I'm not going to assign anyway, but do you see generally which way you would go with that? Okay. The thing that is really the nastiest part of there is I could do the, like that. I know what the, well, do I? Yeah. When y is equal to -1, sine would have to be, you choose which, I would say -pi/2. So that would be my limit here. But when y is equal to 0.8, then you have an inverse sine of 0.8. And it's a pain in the neck to do, but you can do it. But I'll leave that. Since they didn't bother to do it, we'll not bother to do it either. Sorry about that. And we've already done the rest of this. That finishes pretty much 8.4. Homework exercises here. Do either 3 or 5. They're both at calcchat.com. Do either 7 or 9. They're both at calcchat. 7's at calcview. Either 11 or 13. They're both at calcchat. 15 or 17, both at calcchat. Any of the odds 19 to 31, they're all at calcchat. 19's at calcview. Do either 33 or 35, they're both at calcchat. 35's at calcview. Any of the odds 37 to 41, they're all at calcchat, and 37's at calcview. Then there's 43 and 45 under exploring concepts. Number 43 I think is pretty straightforward. Some of you don't have your books. Let me just do that because it's so important, I think. Okay. It feeds off of stuff that we just did. This is page 547. This is 8.4 exercise. And this is number 43 at the bottom of the page. Okay? All it's asking you to do is to state the method of integration you would use to find the integral. Okay? Do not integrate. So we can do this. X times the square root of x squared plus 1 dx. What would you use to integrate that? Yes, not trig substitution, substitution. And your substitution would be let u equal the inside of the most complicated part, x squared plus 1. du would be 2x dx. X dx is 1/2 of that, so yeah. And it's just a real straightforward, simple integration. Okay, I just want to do that. Comparing methods is doing almost, not quite the same thing. Yeah. But anyway, I'll let you fiddle with that. There's true false, 2 of those, either 47 or 49. Think through those. 51's a pretty good problem that, so I'll let you take a look at that. 53 is one like we just did with arc length, only different, okay? 55, volume of a torus. If you want to take that one on, you certainly can. And 57, centroid. If you want to do that one, you can. Here's one like we were just describing, only that was dealing with pressure, this is dealing with volume, but I think you could probably do that fairly easily. Well, not easily, but you can do it. Field strength, no, I'm sorry, that's even. They have a shape there, a traxis. You can look at that if you want. 63 is a fluid force. And you can certainly take a look at that if you're interested. 65 is verifying a formula. I'll let you decide whether you want to do that. 67 is the area of a lune. It sounds like a moon, but it's something not quite the same. It almost looks like a moon, but 67, I'll let you decide that if you want to go with that. All right, that ends 8.4. Any questions on 8.4? Okay, let's move on to 8.5. And again, reminding you what these are. These are integration techniques. Okay? And so far, what are some of the ones we've looked at? Integration by parts, the biggie. Substitution we've been doing all along. I think y'all, most of you came in with those that already under your belt, but we've been doing enough of those. That is certainly a technique. And then trig substitutions and trigonometric integrals. So now we're going to do another one. Let me get this to the current slide. And, whoa, went right to partial fractions. Okay. Our objectives here is to understand the concept of partial fraction decomposition. We're going to be decomposing it here, okay? Could be a little future. Okay. We will use partial fraction decomposition with linear factors to integrate rational functions. And we'll use partial fraction decomposition with quadratic factors to integrate rational functions. So we got a couple of different things to do. The procedure for decomposing a rational function into simpler rational functions, to which you can apply basic integration formulas, is called the method of partial fractions. So let's just see. What if you had a problem like that? And you think of a technique that would work, that we've done so far? That sounds like a good thing to do to begin with. Factor that integrand, especially that denominator. And what would that give you if you factored it? My pen, okay. This would be x minus 3 times x minus 2. Very good. So then you would write that in the integral. 1 over x minus 3 times x minus 2 dx. Can you integrate that? No. Okay. But you made a really good first step to what you can do to really integrate. Okay? Because you see this has a product in the denominator, I am convinced that somewhere out there there's some fractions. Okay, let me write that denominator, 1 over x minus 3 times x minus 2, that there's probably somewhere out there two fractions. Let's just call it a over x minus 3 plus b over x minus 2, that you could come up with two fractions that will add together to be this, because there's the least common denominator. You just have to get the right coefficients up here so that these will add and work that way, right? And if you did that, then I can integrate that. Even I can. Okay, what would this be? Anybody? Integral of 1 over x minus 3 or some other number over x minus 3? The antiderivative of 1 over something to the first power. Second? Someone said something? ln, you got it. That is what integrate as ln's. So now we have something to shoot for. Okay? If we can come up with the a and b there, we can do that integration. That looked impossible before. Now, I was wondering if some of you were going to say complete the square. I'm glad nobody did. Okay? I wouldn't want to go that route. Okay? So let's go with this. Okay? Now, they're not, I don't think they're doing this yet. Let's just see what they do. Let's move on to the next slide. To find that integral without partial fractions, you can, oh goodness, they're going to do it. Complete the square uses the other substitution. Oh man, I did not want to see that. Okay? I can't even believe they even are showing this. But you sure could do it. Completing the square, you take the middle term, the linear term, take half of that. That would be a minus 5 halves. Square that, that's a plus 25 fourths. So, and I don't even think they did that right. Oh yeah, they did. And when you do a plus 25 fourths, add that to 6, which would be 24 fourths, that'd be 49 fourths. No. You add it, then you subtract it then. So, you added, what do I call it, 25 fourths. Yeah. And you subtract that from 6, which is 24 fourths. Oh yeah, 1/2 squared, okay. It gave you 1/4, okay, minus 1/4, okay. And I just can't even believe they approached it this way. But you sure could. Here is your secant theta is equal to this thing. They took the square root of 1/4 and made it 1/2. Yeah, square root of 1/4 and 1/2, so that's your coefficient there. So your trig substitution, the secant theta being this, is 1/2 the secant, because this is your coefficient. Secant theta, and then you do your dx and your tangent theta, you do all the things up here. Oh, what a mess. What an incredible mess this is. Okay? But they did it. Okay? And as you continue, it goes to this and to that, and ultimately gets to that form there. Real easy way to do the problem, right? Not really. Okay? But you certainly do get there. Okay? Believe it or not, you get there. I'm not about to reproduce all that. Here is the easier thing. Okay? And now they cheated on you. They said, now suppose you had observed that this was true. I don't think I would have, or even come close to it. So let me go back to what we had before. Okay? Let's figure out what our A and B is. They said you just observed it. I know I wouldn't have observed that. So let's see what we can do here. Now I'm going to show you the easy way to do this. We're trying to get the A and B here, right? So I don't like all those denominators. So I want to multiply, but this is an equation, so this is legal to do in most states. Multiply all three equations by x minus 3 times x minus 2. Multiply this by x minus 3 times x minus 2. Multiply this by x minus 3 times x minus 2. That's a lot of writing, but it's pretty simple. This goes out, that goes out, so you're left with a 1 here. Okay? And there's Justin. Okay. Still missing Ariel, and still missing Jeremy and Clark. I don't think Clark's coming back. Still missing Davis today, right? Patrick and the other Brandon. Okay. All right. So here we have a 1. Here the x minus 3's go out, and here the x minus 2's go out. Okay? So what we have now is 1 is equal to A times x minus, if I could read my writing, I think that's a 2, plus B times x minus 3. Okay? Now, two equations, just too many unknowns here. So here, I'm going to do something that looks like it's not fair. I mean, there's parts of it that sort of print that. Let's just imagine that, say, x is equal to 2. Why not? So x equal 2, this goes to 0, right? And if x is equal to 2, well, there's no x's left over here, so we don't have to mess with anything there, do we? Yeah, I think so. So we have, if x is equal to 2, this would be a minus b is equal to 1, right? You see that? My first try here is just going to say let x equal 2. And that gives me 1 is equal to 0 plus b times negative 1. So 0 doesn't add anything. Divided by here, b is equal to negative 1. Got it? Okay. Then, back to that original thing, let's just say, what if x is equal to 3? Well, now this goes to 0, and you have 1 is equal to a, because 3 minus 2 is 1, right? So a is equal to 1. So let's go back to our formulas here, and then you would have 1 over x minus 3 minus 1 over x minus 2. And we're claiming that's equal to 1 over x minus 3 times x minus 2. Hey, what they said was true. That is exactly what that is. Now, if this is what we're integrating, then we integrate each of these, dx, dx. And y'all already told me what that would be. What did you say it was? This first integral is ln of absolute value x minus 3 minus ln of absolute value x minus 2. And then you can do your plus c out there. And notice, with this fairly simple, just done on a little bit of a page here, we can replace that half a page, well, more than half a page, that entire page, and there we get the same answer. The log of absolute value x minus 3 minus the log of absolute value x minus 2. And let me tell you something else. They skipped a bunch of steps. So, much easier to use partial fractions than completing a square. Way easier. Okay? Now, they said, oh, perhaps you observed this. No, we didn't, but we could come up with it. We did come up with that. And then we did the integral. And there we get it in, with big writing and everything else, in a fraction of the time it took us to do completing the square. Okay? That is the method of partial fractions. This method is clearly preferable to trigonometric substitution. Amen, brother. Okay. Its use, however, depends on the ability to factor the denominator to find the partial fractions. If you can't, then you are left with trig substitutions. And then don't expect any easy answers, as if that last one was easy. We know that from algebra, every polynomial with real coefficients can be factored into linear and irreducible quadratic factors. So we can't get them all to linear factors, but we can get them to linear and irreducible quadratic factors. We can still do this. So here's one. Uh-oh. What a mess is that? X squared plus x fourth minus x minus 1. Is there any way we can factor that? Okay. Well, I was going to say factor by grouping. That's exactly what they did. Skipping a few steps here. Let's start back up here. Group these two and those two together. In the first group, what can you factor out?
4 x's.
Say again?
X to the 4th.
X to the 4th. And what do you have left? X plus 1. And in the second group, what can you factor out? A minus 1. And what do you have left? X plus 1. And then, what can you factor out of that? X plus 1. And what do you have left? X to the 4th minus 1. And can you factor that any further? X to the 4th minus 1. Second? Yep. What did you say? X squared minus 1 times x squared plus 1. Can you factor that any further? Yeah, you mean here, x plus 1 times x minus 1? Sure you can. This one? No. That's what they call irreducible quadratic factor, x squared plus 1. Can't take that any further. So let's regroup those slightly. That would be a x plus 1 squared times a x minus 1 times the x squared plus 1. Sure enough, there it is. Oh, they did it down here too, didn't they? Okay. See how that works? We got the same thing they did, slightly different order. We got linear factors, one of them is a multiple factor, and an irreducible quadratic. Okay? So sure enough, that can be factored that way. That was a real special one because you could use factoring by grouping. But they say, we know from algebra that every polynomial with real coefficients can be factored into linear and irreducible quadratic factors. They didn't say it would be easy, but they said it can be done. Okay? Now, x minus 1 is just a plain linear factor. X plus 1 is a linear factor, but it's repeated, and x squared plus 1 is an irreducible quadratic factor. Okay, using that factorization, what if you had a partial fraction? What if you had a rational equation that was some n of x over this thing? Knowing that we can factor that denominator. We just did it, okay? Well, that n of x is a polynomial of degree less than 5. If it's equal to 5, guess what you got to do first? Long division of polynomials, right? Which is kind of a pain in the neck, but it's doable. So if that had been x to the 7th or x to the 5th or x to the 14th, divide this into that. Whatever remainder you have is now going to be something with a degree less than 5. So let's assume that's what we wound up with. Okay? Now, they're throwing several things at you right now. This n of x, okay, forget the numerator for now. This part would be some a over x minus 1. This part with two factors in it will be a b over x plus 1 and a c over x plus 1 squared. Now that doesn't quite seem fair, but that's what happens, okay, when you have a multiple. If that had been x plus 1 to the 5th power, it would be b over x plus 1 plus c over x plus 1 squared plus d over x plus 1 cubed. Keep going until you get to the last one, okay? And then this one, because it's a quadratic, its coefficient is 1 less degree, dx plus e over x squared plus 1. Okay? Ew.
You get a break after that.
What's that?
If you get a break after that.
Oh, that's true. Okay. It is about that time, isn't it? Didn't we have a break earlier, or was that the other class? Yeah, that was my other class. Okay. I'm going nuts today. All right. We will continue with this one, though. So, all right. Let's, before we get going back where we picked up last time, pick up where we left off last time, there's a blurb on page 650, very first page of this section, and the blurb is on John Bernoulli. Now, I'm not absolutely certain that it was John. I think it was Johann, but, you know, that would be the thing. Pretty interesting family here. I can't remember for sure, but I believe he's one of two brothers. I can't remember the other brother's name right now. Both absolutely brilliant mathematicians, okay? And then they had some kids. And I don't remember how many, which one had or the other, but some of those were very brilliant mathematicians and physicists. And from what I understand, that family competed like crazy with each other. And they were not really nice about it sometimes either. I mean, it wasn't a friendly competition. It was cutthroat, you know, almost. I remember the story, one of them, it may have been this one, who had applied for this prize, knowing he was going to get it because he was about the best mathematician in Europe at the time. So he was pretty sure he was going to get it. He didn't know that, I believe it was his son, also submitted an entry and beat the dad. And the dad was so furious he kicked the son out of the house. You know, so, you won the prize, you live on your own. So anyway, I believe it was this one. But they were a whole family of very bright people, okay? You'll see Bernoulli stuff all over the place. The only trouble is you never know which Bernoulli it came from. There's Bernoulli's principle in physics. They use aerodynamics and things like this. It's how planes fly, basically. That was Daniel Bernoulli, which was one of the second generation, I think, okay? But John Bernoulli was a professor at the University of Basel, Switzerland, taught many outstanding students, the most famous of whom was Leonard Euler, who was probably one of the most prolific mathematicians of all time. So, yeah, this some pretty hefty folks back then. Now, why am I saying that? Well, remember, you do have a research paper due, right? Right there where I mentioned several possibilities. One is this guy, John Bernoulli. One is Leonard Euler. One is the brother of this one, whatever his name is. Another was Daniel Bernoulli. There's Bernoulli's principle. There's Bernoulli's equations. There are Bernoulli all over this place. You know, lots of topics to choose from right there from this one little blurb. But I would, the reason I'm mentioning this is my largest class, I think, of all the classes I'm teaching this summer. Doesn't look like it now, does it? And I've gotten one paper in so far. And we're more than halfway through the term now. I mean, midterm was sometime this week, so I think we're past midterm. So you only got basically the month of July left. Please don't put it off till the very end. It's just going to be far easier to get it done earlier than later. Okay. And let me also say your first test y'all have had for a little bit. We are rapidly getting close to the end of this chapter. And when we get to the end of this one, you're going to have your second test. I'd rather have the first one in before I pass out the second ones. I won't hold that to you, but if you made any errors on the first one, I don't want you repeating those errors on the second, but if you haven't turned it in, you're not going to see what those errors are, okay? So please, don't let the term go by without getting too far behind. Otherwise, things really pile up badly at the end. Okay, so we got to here. This is about the middle of page 551. Let's go to the next slide. Now, what do we do with something like that? I've already given an indication, okay? One thing I would do was multiply both sides of the equation by this times that, you know? Both sides. That will wipe out your denominator here, but it leaves you this numerator. And that may have x's in it, just not, fourth degree or less. That's good be. Okay? And here it would wipe out this part, but then you'd have all the rest of these is with your A. You have these and one of those with your B. You would have this one with your C, and you have these three with your D times that. So you got a pretty hairy looking thing there, but then you use the trick of letting x equal 1, and that'll wipe out, because all these will have factors of x minus 1, that one, that one, and that one. So basically you can figure out what A is right there, okay? Of course you put x equal 1 in this side too. Now the x equal minus 1 will knock out this, and that one, because they'll have factors of that, but you can figure out what C is from that. And unfortunately, that's all you can do. The rest of them, you're going to have to do some pretty complicated, well, not complicated, a bit more work to get those other coefficients. But you knocked out 2 of them already, and now you got 3 to go. And frankly, how to do that is a 3 by 3 matrix. Have any of you done any matrix algebra? A little bit? Okay. Hopefully they won't give us many of those, but I'll show you how to do them if they do. Okay? So, here is the procedure for the decomposition of these partial fractions. Now, if that numerator turns out to be more than a higher degree than the denominator. In other words, that makes it an improper rational expression. I don't want to call it a fraction. They're not fractions, rational expression. If the degree of the numerator is greater than the degree of the denominator, divide. Okay? Divide. Okay? Divide the denominator into it, and then you'll get a polynomial here. If this was 3, had an x to the 7th in it, and that only had x to the 4th, then you're going to have a third degree polynomial here, and then you're going to have a new numerator, which is going to have to be less than the degree of the denominator. And then we proceed with this. This polynomial we can integrate with no problem. Okay, just go and integrate. No sweat there. Then we'll proceed with partial fractions of just the remainder. Okay. So ultimately that n sub 1 will have a degree less than d, and then you apply the rest of these steps to that. Okay. Now, if you have numerator of less degree than the denominator, either up here or here, wherever you have it. The next step is to completely factor that denominator. Okay? And that denominator may have this form. This is rather complicated looking, so don't get too frightened on it. Px plus q possibly to the nth power. And or ax squared plus bx plus c, possibly to some nth power. But this is irreducible. That's something, if you did try the quadratic formula on it, you're going to get complex numbers. You can't reduce that. If you did quadratic formula on it and got irrational numbers, yeah, you're going to use that, okay? But then you get back into this one. But if you can't reduce this, that means that would come out being not just irrational numbers, but complex numbers. You have i's in it. Okay. Now, all those that look like this, where the m is 1 or something bigger, okay, these are, list those separately, okay? Now, if you have more than one of these, the first would be a1 over px plus q plus a2 over px plus q squared plus all the way up till you have a sub m over px plus q to the m power. Now, this is really complicated looking, but that's what you do with all these linear factors. A lot of times that's just going to be a 1, so you just have a over that, okay? But if you do have more, you string them out like that. For these irreducible quadratic factors, your numerator is going to be linear forms. Bx plus c, b1x plus c1, bx2 plus c2, for all the powers of that up to n. Okay? So that's what your thing would be. So that explains how they got the previous one. They just threw that on you and said this is what it is before they gave you the rules. Okay? Now, again, this is fired at you fast and furious. I think when you start doing them, you'll see it's really a little easier than what it seemed. Okay, so let's start with the linear factor ones. Those are going to be generally pretty easy. Write the partial fraction decomposition for this. We're not integrating anything right now. There's no integrals involved. We're just going to do that. We've already done that one, haven't we? That's the first one we did, right? Okay, so anyone remember what it was? Three minus 1 over x minus 2. You factored that first, x minus 3 times x minus 2. Then you did the decomposition, go to it, you got it not. Okay? That was not bad. All right. Didn't think we had lost you, but I was hoping we hadn't. Okay. All right. We had already done this one, so we're moving on from there. Okay? We did it. Let's see how they did it. So if I can get it to erase. Okay. First, they factored the denominator, just like we did. And then we did one partial fraction over the first factor, and another partial fraction over the second factor. Okay? A and B, we're going to figure out. How do we figure them out? Okay? What they do is multiply both sides of the equation by the completely factored form, x minus 3 times x minus 2. That wipes out this whole denominator, leaving you just a 1 here. And when you multiply this, wipes out x minus 3 for this one, leaving you a times x minus 2. And that one wipes out x minus 2, so you have b times x minus 3. Okay, there's your basic equation. Okay. Now, what you could do is multiply those through and then solve for a and b. Okay? It's hard. I mean, it's long, tedious, and stuff. The quick way is to just assume, because that equation is true for all x's, you can substitute any convenient value for x to obtain equations at a and b. And that's what we did. Now, back when I was doing it, I said it doesn't seem fair to do, to let x equal 2 and x equal 3. It just didn't seem right. And here's why it didn't seem right. Because you know that x can't be 3, can't be 2. Because look at them, they show up in the denominators. And yet those are the very values we use here. Because you see, you've gotten away from that, and it still doesn't seem right, but it works. So I'll take it, okay? It can feel as bad as it wants to feel. If it works, I'll still do it. And it does work, and it makes it so much easier, okay? So it says you can plug in any values you want to. It doesn't seem like you should be able to plug in values that were not allowed at the beginning. But it says you can, it works. The most convenient values are the ones that make the particular factors 0. Yeah, that's going to do that. It would have also made the denominator 0, but we don't worry about that, okay? So to solve for a, let x equal 3, which is going to wipe out your b, because this is going to be 0, and this gives you simple a times 3 minus 2 is 1. A times 1 is a is equal to 1. There you have it. A is equal to 1. Okay? And then, just as simply, we let x equal 2, which is going to wipe out our a1 here, and this will give you minus b is equal to 1, which means b is equal to negative 1. And they show you the complete math for it, okay? So the decomposition is simply 1 over x minus 3 minus 1 over x minus 2. A was 1, b was minus 1. There it is. And that's what they had at the beginning, okay? Which is said, you might see this. No, I didn't see it, but it's easy to get to. Okay. That's all they do in example 1. They skip example 2. Okay? So let's us do. The one they chose to do was pretty straightforward and simple. Let's see which one they skipped. Okay? Find the integral of 5x squared plus 20x plus 6 over x cubed plus 2x squared plus x dx. Oh, that's almost as easy as that other one, isn't it? Yeah, right. Okay. Where would you begin? Factor what? The denominator. Before I do that, though, I'd already done it, and you probably already did it too. Make sure that numerator is lower degree than the denominator. What's the degree of the numerator? 2. Degree of the denominator is 3. Make sure that's true before you even start factoring. And sure enough, it was. So let's continue as you just said. So factor the denominator. How would you factor that denominator? Pull out an x. And what does that leave you with? X squared plus 2x plus 1. How can you factor any more? Or is it, say again? X plus 1 squared. All right, got it done. There's your factorization of the denominator. What do you do now? Second? Okay, we start with that process. Okay, and that process is this. I'm going to write it out probably in more detail than I would have otherwise since this is our first time. 5x squared plus 20x plus 6. Now, another thing I do is look at that and see if there's anything like common factors. I already did this. 5, 20, yeah, there is, but 6, the 2 and 3, that'll do 20, but it won't do 5. Yeah, no common factors. If there was, get them out of there too, okay? But there's not, okay? That over, I'm going to go on and write this in factored form, x times x plus 1 squared is equal to, now what will we do with the right-hand side? Okay, we'll have a over x plus b over x plus 1 plus, okay, if you want to do c. The book kind of likes b1s and b2s. I don't care. C is just as good for me over x plus 1 squared. Anytime you have a multiple one here, you do 1 for each power up to this power. Okay? But you always have it, if it's a linear factor in the denominator, your numerator's a 0. You know, it's a constant. If you had an irreducible, if this had been an irreducible quadratic, then in the numerator you have a linear form. Okay. And then what do you do now? What do you do now? Help me. Okay, we're going to multiply everything by x times x plus 1 squared. In the numerator, and on the left-hand side and on the right-hand side. X times x plus 1 squared. X times x plus 1 squared. X times x plus 1 squared. Okay? And guess what? With sound effects, everything goes out there, and you're left with, oh, string it out here a little bit, 5x squared plus 20x plus 6 is equal to, over here the x's go out, and you're left with a, and let's go on and maybe not yet. Okay, let's leave it like this for now. X plus 1 squared plus b times, oh, and here, one of these goes away, and you're left with b times x plus 1, right? How about the third one? What are you left with there? C times x, because your denominator goes into that part, cx. All right. Now, what are some easy things you might try? Second? Okay, let's let x equal 0. Okay? On the left-hand side, what are you left with? Second? 6. Over here, what are you left with? Second? A. Because 0 plus 1 is 0 squared, is 1. 1 squared is 1 times A. Over here, what are you left with? 0, 0. So, we got A is equal to 6. That was pretty nice. Okay? Anything else? Let's go back to this one now. What else might we try? X equal -1. Okay, if x is equal to -1, this will be 5 minus 20 plus 6, which is -9. So on this side of -9, on this side, if x is equal to -1, this is 0, right? What would this be? 0. And this would be C, C times minus C, right? X equal negative 1, that'd be a minus C. So guess what this gives us? C is equal to, okay, what did I just do there? Okay, I'm sorry. That just, yeah, that gave us a, so C is equal to, yeah, I had it right. C is equal to 9. Ha! We got 2 of the 3 already, okay? There's nothing else we can substitute easily, is there? So now what we have to do is plug in what we know, okay? Nothing else we can substitute that's going to make it easy. So what we have is 5x squared plus 20x plus 6 is equal to, let's multiply this out. What does that x plus 1 squared give us? Anybody? X squared plus 2x plus 1. Very good. Multiply that out and you get ax squared plus 2ax plus a. You see what I did? Everybody? No magic, right? Okay, let's go to the b term. Let's go on and multiply those two together. And what did they give you? X squared plus x. And multiply that. And that'll be plus bx squared plus bx. Buy it? Okay? And then the last is just plus cx. Okay? Let's combine some like terms on the right. So 5x squared plus 20x plus 6 is equal to, oh wait, what am I doing? Okay? Sorry about this. I meant to substitute in. Well, I can substitute in now. Okay? A is 6. So why carry around a's anymore? This is 6x squared. In fact, let me go back. I don't have enough room to mess around with this. Okay? I meant to do this and I completely forgot. Okay? Okay. This will be a 6. This will be a 12. Remember this for me here. Okay? And this will be a 6. Okay? Let me write those in before I forget. 6, 12, 6. Right? And the b's are not. No, the b's we don't know. The c is a 9. So let's erase the 9. A c and make it a 9. Okay. Don't reproduce the wheel if you don't have to. Okay. Now I think we're in decent shape. Okay. Let's look at the x squared terms only. Over here we've got a 5. Over here we have a 6 plus b. Guess what? B is equal to, second? -1. There's our B. Now, that seemed way too easy. I want to verify it. You don't have to do this, but I'm kind of paranoid that way. Okay, let's look at the linear terms. Here we have a 20 is equal to 12x. Well, no, we don't need the x. Sorry. 12 plus b plus 9, right? And 12 plus 9 is 21. B is equal to -1 again. Whew, that makes me feel better. But you know I'm still a little paranoid. So let's look at the constant terms. 6 is equal to 6. Huh. I'll buy that. There aren't any b's in that. So I'm convinced b is equal to -1. Okay? Now that we've got those pieces of information, I'm going to erase a lot of this scratch work because I just don't have room for it. Okay? Is that okay? You feel comfortable with that? Okay. What do I want to keep? Okay. 6 equals 6, I can remember that. Okay. I'm trying to think if I need any of this. I probably needed that. Yeah. But I'll leave it in this form. Oops, I erased more than I wanted to there. Don't need that anymore. And if I can get that erased. There we go. Okay. And now I don't need this. I do need that. And I don't need anything here but that. Okay. All right. So what I'm going to do is rewrite my integral as 5x squared plus 20. Oh, no, I don't need all that. Let me just get down to the brass tacks here. 6 over x, because a was 6. I'm going to write it as dx plus the integral of minus the integral of b was minus 1, that's why I changed that. 1 over x plus 1 dx plus, I'm going to pull the c on the 9 on the outside, over x plus 1 squared dx. Okay? Probably should have done the same thing with the 6 there. Isn't that the same integral we had here? Oh, this thing here came out to be that with these coefficients, right? And that's what this translates. Okay, I'm going to pull that 6 on the outside. Can we integrate that first one? Yes, what is it? 6 times the ln of x, right? Okay? Don't add c's everywhere. Let's just wait till the end. Okay? Minus, how about the next one? ln of x plus 1. I'll put those in absolute values for now. Plus, how about this one? 9, what would that be? Really? Okay, I'm sorry. I did forget my 1 over. Sorry. Whew. That was not good. What you reckon that's going to be? Huh. Second? Okay. 9 times the integral of x plus 1 to the minus 2 dx. That better? I like it better. It's 6 log x minus log x plus 1 plus 9 okay, it's what it comes out to be with one little difference. Yeah, you have a negative there because your n plus 1 would be a minus 1, and that's what you're dividing by. Okay, so that, skipping a few steps, that's what it gives you. Okay, and now we can do our plus c. So let's see if we can write this. Can I go on and erase these? I think we're okay with them. All right. Let's see if we can get this in a little bit nicer form. I don't know if this is any nicer or not, but I kind of like it better. This can be written as log x to the 6th power, and then those two can be the log of x to the 6th over x plus 1. Now you might want to leave the absolute values in there. I don't know. with the x to the sixth, that's going to be positive no matter what it is, so we're okay with that. Minus 9 over x plus 1 plus c. Okay? Now, I don't know if they simplified that far, but let's see. Oh, yes, look at that. Well, they did leave the absolute value bars here. You didn't have to. You could just put them in the denominator. That would be fine. The log of x is 6, absolute value of x is 6 over x plus 1 minus 9 over x plus 1 plus c. Got it. So that wasn't nearly as bad as it looked like it would be. I mean, when you looked at that thing, thought, oh, what a mess. And it was a little bit of a mess. Okay? But break it down, do the things that you can, get the easy things done, like figuring out what your A and your C were. B was going to be a problem, but if you got 2 out of the 3, then use that whole coefficient, plugging in the A and the C, and all you have to do is figure out what B is. And you actually have 2 ways to figure it, with the x squared terms or the x terms. The linear terms didn't give you anything useful. 6 equals 6. It's good to know, okay? You don't want to be in something else. But, yeah. And then your integration wasn't too bad after that. Was it? All right. Let's now, oh, yeah, okay. Let's now move to quadratic factors, okay? How are we doing? Oh, when using a method of partial fractions with linear factors, a convenient choice of x immediately yields a value of one of the coefficients. Okay? Most of the time. With quadratic factors, a system of the linear equations usually has to be solved regardless of the choice of x. No shortcuts there. Okay? Use any that you can, but you're going to be run out of options fairly quickly. Okay, so let's go to example 3. And by the way, this one is one that you can see LarsonCalculus.com for an interactive version of this type of example. I don't know if it'll be exactly this, but it'll be this type. So here's what we're asked to find, and thank you very much. They did at least start factoring the denominator. They could have not done that for you and left it for you to figure out how to factor. Thank you so much for at least beginning. They don't have it fully factored, but they at least have it started. Okay? Now, what else do you notice about that?
It looks like power
the what?
Power is higher than
One more?
the H2H3 is higher than the H2.
Well, not quite. Because you see, this is the x squared times x squared, it'll be x to the 4th. So yeah, good. That's the first thing to look for. But remember, you can, if you multiply those back together, that would be x to the 4th, and that's more than x to the higher degree than x to the 3rd. So you're okay. And what were you saying? Was it something else? Same thing. Okay. Now, what else do you notice? It sort of irritates me for them to do this to you, but they did it.
You take 2.
Yeah, factor a 2 out of that numerator. Why carry around bigger numbers than you need to? Just don't forget you factored it out. Okay, so that's the first thing I would do. Well, that's one of the first things. So I'm first going to factor out a 2 from the numerator. And what would that leave me with? X cubed minus 2x minus 4. There's your numerator. Now, we've still got some factoring to do in the denominator. What would that give you? X times x minus 1. Can you factor that next one? No. X squared plus 4. Okay. So, what would you try next? I'm going to drop the integral sign into dx's for a while, just deal with what's on the inside. In fact, I think I'll take it up a notch. Not as Emerald does, but here. do x cubed minus 2x minus 4 over x times x minus 1 times x squared plus 4. Now, how am I going to try to break that down? A over x is a good first start, plus b over x minus 1, that's a good start, plus, okay, this one, because that's an irreducible quadratic, you can't factor it any further, you have to have a linear in the numerator. So what you say, cx plus d, that's fine with me, I don't care what you call them. Just don't use the letter you've already used before, and that's over x squared plus 4. Okay? Now, what's your next step? Multiply by your denominator. So this will be, I'm not going to write it out. It'll just wipe out that. Is that okay? Okay. And here it'll wipe out this part, but leave me an x minus 1 times x squared plus 4. Right? And here it'll wipe out this part and leave me an x times x squared plus 4. And over here, it'll wipe out this part and leave me this times x minus 1, which I'm just going to write it as x squared minus x. You okay with that? You see what I did? Not too magical, right? Multiply by that whole denominator, which is going to wipe it out here. And this will wipe out this part here, leaving these parts. This will wipe out this part, leaving those parts. And this will wipe out this part, leaving the product of those, which I went on to multiply. So it's easy to write it out. Okay. Now, what would be, I'm going to write that out a little bit neater. Is that okay? X cubed minus 2x. Yeah, okay. I thought I missed a term there. 2x minus 4 is equal to a times x minus 1 times x squared plus 4 plus b times x squared plus 4. I'm purposely not multiplying those. And I probably shouldn't have done the others either. Well, I don't have any more room than I did before. Cx plus d times x minus 1. I went back and put it back in. Sorry about that. Okay, there's a reason for the madness though. Now, what would you do next? Besides erase my right and write it nicely. Say again? Okay, and how would you do that? Okay, let's first say let x equal 0, but don't use that pen on my board. Okay, let x equal 0. All right, what will you have on the left-hand side? -4, right? Okay. What would you have on the right-hand side? First term? -4a. Does everybody see that? X equals 0 would be a minus 1, a plus 4, that's minus 4 times a, minus 4a. On the next term, 0, next term, 0. That's why I went and factored that out again. So guess what that tells you? A is equal to 1. Ha, that's not too bad. Okay, now let's go back to this one and do what? Let x equal 1. So what do we have on the left-hand side? -5 is equal to, on the right-hand side, first one 0, the next one will be x is equal to 1, second, 4b. or not for B. Okay, no, never mind. And then the last term, 0, isn't it? Okay, because you have x minus 1 there. It's hard to read, but it is. Okay, what does this tell you? Negative 5/4. Now that doesn't feel very comforting, does it? Let me make sure I haven't done something stupid. I know that I was afraid it'd come back and bite me somewhere. I'm afraid it has. Okay? I think we're still going to be okay, though. So let's live with it. But what can we do? There's no other simple substitution, is there? Okay? Well, let's figure out what we can do now. Let's multiply through with what we got. X cubed minus 2x minus 4 is equal to, your A is 1. So we need to multiply these two together, which is basically foiling them, right? That's x cubed, right? Minus x squared, that's those, plus 4x, that's those, and then minus 4. Okay? And B is yuck, minus 5/4. I'm hating it. Okay, so that's going to be yuck. I would say let's go put them back in, but it's too late now, I think. So that's going to be a minus 5/4 x cubed minus 5x, right? You see what I did? The B was 5/4, and the x cubed term is just negative 5/4 of x cubed. But then here the 4 will cancel out the 4 down here, so it's minus 5x. Okay. Now, unfortunately, this one is not nearly so nice. But I'm going to go back and multiply those two together. I factored them out here, but I'm going to go back and multiply those two. So this is going to be a cx cubed. Okay. And falling this way, that's a dx squared. Right? But we also have a cx minus cx squared. Right? Dx squared minus cx squared. And then we finally have a minus dx. Sorry about that. Okay. I think I got them all in, don't I? Okay. So let's look at the x cubed terms alone. Okay. Well, that first one, you can subtract the x cubed from both sides and just wipe those two out. Okay. So that leaves you a 0 here. So 0 is equal to 5/4 plus c. You're right. Minus 5/4 plus c. Okay? So that means c is equal to 5/4, because that's the only x cubed terms we had. Right? So let's go to the quadratic terms. You don't have a quadratic term here. So that's another 0 is equal to a minus 1 from here plus d minus c. But c was 5/4. So let's make that a minus 5/4. Right? Okay, this stinks, doesn't it? So that's going to be a minus 9/4 on the left. Add it to the right, so this produces D is equal to 9/4. Got it? Let's do the linear terms, because we got everything we need, but let's just check and make sure they're working. Minus 2 here is equal to 4 there, minus 5 there, minus D there. Okay? Well, 4 minus 5 is minus 1. Add that here, and you get... Oh, please tell me this isn't checking, is it? Yuck. This gives me a different D, doesn't it? Linear term. Have I missed a linear? Oh, there it is. I'm sorry. No, that's it. I got that one. How did I wind up with nothing linear in B? It can't all be because I factored out the 2. There's something else wrong here, and I just don't see it. And it may be something way back at the very beginning that I messed up. So sorry about this, folks. Let's see, let's see how they are stacking up. No, there's some problems here, I think. Wait, no, I'm looking at the wrong page. Okay, sorry. Well, let's first see if they named them the same way we did. I think so. Yeah. So the basic equation is this. A is equal to 2. We got 1, but that's because we factored out a 2. So that's okay. They get B is equal to negative 2. And in my thinking, it should be a negative 4. So when x is equal to 1, 1 minus 2 minus 4, that would be a minus 5. That's right. And this would be a 0. That would be 4 times b. I don't see any other way. No. X is equal to 1. 1 times 5. How did I do that? That's a 5b. Up here, x equal 1. B times 1 plus 4 is 5, not 4. So that's a 5b. How did y'all let me do that? Okay, so B winds up being a negative 1. I knew that didn't look right. Okay, B is negative 1. Oh, man. Now, this just shows how sad it is when you mess something up and how it will just mess up your whole life. No, I'm just kidding. I'm going to change that one too. I think the rest of them are going to be okay. So let's see if we can minimize our damage here. Okay. That would be A is equal to 1. We got that one. B is equal to negative 1. So that would be a minus x cubed minus 4x. Is that right? Yeah. And then the rest of those. Okay. Okay. That's just... Okay, I'm going to start over here. It'll be easy enough to do. Let's look at the x cubed terms. So first we'll just subtract these off like we did before. And then we have 0 is equal to minus 1 plus c. So that would say c is equal to 1. Okay? Done. Then we'll do the quadratic term. 0 is equal to negative 1 plus d minus c. But c is 1, so that's a minus 1. So that would be d is equal to 2, right? Now we're going to check. Negative 2 is equal to, I did the quadratics here. Okay. The linear terms are negative 2 equal to 4 minus 4 minus d. And d is 2. Sure, that checks. Let's do the constant terms. Minus 4 equal minus 4. That's it. Okay. So yes, it does check now. Our numbers are okay. So now, sorry about that. I didn't think the 2 was going to do that to us. I sure didn't. Hoped it wouldn't. So let's see what we got now. 2 times the integral. Okay, go back to your original thing here. The integral of a, which is 1 over x. That's 1 over x dx. Okay. The b is a minus 1, so it's going to be a minus the integral of 1 over x minus 1 dx plus c is 1 and d is 2, so that would be the integral of x plus 2 over x squared plus 4 dx. Look right? Y'all better be watching me. Okay. What's the first one give you? Second?
Let you multiply all the integrals by 2.
Don't I do what?
Let you multiply all the integrals by 2.
Yeah. Yeah. Sorry. I didn't put my bracket in. You're right. Okay. Now, this will be 2 times ln x. I'll put that in absolute value bars. Minus ln absolute value x minus 1. Okay. Now, this last one. Let's do a timeout here. And I'm going to have to erase some stuff because it's just too messy. Okay. Going to do a lot like I did before. Just leave my basic form here. Okay, not that I need that anymore. I think we've already substituted all these in, so I'm going to get rid of all these. Probably don't need that top one, but can't even read that anyway. Okay. What I want to do is get it so I can see what we're doing with this last one. Okay. Now, just understand I've still got something to do here. I'm going to take this one up here and do the integral of x plus 2 over x squared plus 4 dx. And ask you, how would you go about doing that integration?
Substitute or you could.
Second?
You could substitute or break it out.
Okay. Definitely a substitution will be somewhere, but I think breaking up is hard to do, but let's do it first, okay? So that's my suggestion. Integral of x over x squared plus 4 dx plus the integral, or 2 times the integral of dx over x squared plus 4. Okay? This one, the first one, you nailed it. Substitution. What would be your substitution? Okay, let u equal x squared plus 4. Then du is equal to 2x dx. We don't really want a 2x, so let's divide by 2. And that gives me a du over 2. So this would integrate to be 1/2 times du over u, right? Which would be the same as 1/2 times u integral of u to the minus 1 du. What would that integrate as? That's ln u. I didn't need this. That was ridiculous. Ln u. But what is u? What are you? No, what is x squared plus 4. That I don't need absolute value bars. Okay? Ln of x squared plus 4. All right. That next one, though, what you reckon we're going to do with that? Don't think so. Because you don't have a 2x. Huh? Say again? Okay, as in plus 2 times integral of x squared plus 4 to the negative 1. Does that help us any? I don't think so. Do you think maybe a trig substitution? It doesn't have a radical on it, but who knows? That's the closest thing I can think of. What would that be then? So I'm going to undo what you just told me to do. Whoa, probably too much. Let's do a trig substitution. Okay. All right. Let, what would you do? Which one's that? X equal? Second? Tangent. Only 2 tangent theta. Then dx is equal to? Second? 2 secant squared theta d theta. I don't have room to do all my usual stuff. The x squared will be, x squared is going to be 4 tangent squared, right? Have we run out of time? See people start, ooh, we have, haven't we? Okay, let's try to do it quickly here if we can. And then when you add 4 to it, that would be tangent squared plus 1, so that would be 4 secant squared theta, right? Okay, so we have in our numerator 2 times the integral of the dx is another 2 secant squared theta. Okay, d theta. And in the denominator we have 4 secant squared theta, right? And guess what? This will be a 1/2 times 2. It looks like just a d theta, okay? So that's just going to be theta. And what is theta? Theta is the arc tangent There it is. Arctangent of x over 2. Okay, so this last one will be, this will be a plus 1/2 ln of x squared plus 4 plus, what did I just say? Inverse tangent of x over 2. And then maybe a plus c somewhere out there. Multiply by 2 and you get ln of absolute value x over x minus 1 squared. That will wipe this one out, plus ln of x squared plus 4, which we probably could combine, but I'm not going to right now, plus inverse tangent of x over 2 plus c. So let's see how close we got. Which one were we working on either? Here we go. So they kept the 2 there. 2 log x, 2 absolute value x, plus 2 log absolute value x minus 1, plus, and the 2 canceled that one out, x squared log x squared plus 4, plus 2 arctangent, oh, I left off my 2. That 2 right there I forgot to bring down. 2 arctangent, I think, x over 2 plus c. Okay, good deal. We will start next time on repeated quadratic factors. So we'll do that. Let me see what homework exercise. We came close to finishing 8.5. Any of the odds 3 through 19, they're all at Calc Chat. 7's at Calc View. Do 21 or 23. They're both at Calc Chat. 21's at Calc View. Goodness gracious. I don't see. We'll stop there and we'll look at the rest of them when we get closer. Okay. They jumped a rabbit there, or a shark or something. Okay, good deal. Be working on your papers, be working on your first test, be doing these homework exercises, and have a good weekend to boot. Right? That'll make it good to be working on calculus.
I'm going on vacation next week. I'm not going to be here Monday.
Okay.
We're not going to be handing out the next test Monday, are we?
I don't think so, but if so, I'll give it to you the following Monday, because we're not here Wednesday.
Yes, sir.
I'm sorry, this Monday,
Yeah.
I had work.
Okay.
Next day, I didn't get my license again. So, I just go online and write down the notes for Monday.
Yeah, you can follow everything we did on Monday. Hopefully
Yes.
it'll be out there.
Thank you.
Yeah.
Yeah, I said.
No, you too.